Alrighty then. Yeah, what's going on? Memes here. Yeah. So today I'm hopefully actually going to get to that thing behind me that I said I was going to get to at some point, but we ran out of time. It was all right. We were having some fun. So yes, we're now on a slightly different scheduling thing because we're stuff going on earlier, but yes, we can see Charlie has joined us. Good to see you, Charlie, my friend. Yes, yes. Okay. I should probably erase the other things. Well, number one thing is we have light kind of blocking them. But we'll make room for some other stuff. This is something that kind of got my noggin jogging. And it was a behind the scenes conversation of a certain, perhaps we'll say maybe mad scientist. Okay. And I got to thinking because there's all these different ways you can write these different formula and stuff like that. And well, sometimes you might be able to better interpret some things than others. Well, we'll finish erasing this as we have folks joining us from the YouTubes, the X Twitters, the Blue Skies, the arbitrary Discord servers, and maybe, just maybe, you watch something and the algorithm's like, oh, you should watch this now. I can only apologize so many times, but okay. So let's go into the simplification of different stuff and things. All right, so let's undo this. A little bit more. All right, here we go. All right, marker over here. All right. So we're going to start off. This is going to be a little bit of review for some folks, but this is one of the very interesting things, especially if we're going to lay out a case for why anybody should listen to us. Because number one, you can say all these words. You say like, I've done this. I figured this stuff out. It's like, okay, number one, do you have the receipts? AKA, can you do it? Okay, number one. Now, you can always kludge things together. You can write enough different stuff and add in different things and error corrections and stuff like that. And it's like, all right, you might have a massive expression that gets you the precisely measured number. Number one, if you're getting the precisely measured number itself, you may want to question that because a lot of times you're getting a little bit of a spectrum. Maybe it'll hit on it for a particular measurement, but if that's just be very careful because I feel like sometimes people will adjust things for number. Hey, I'm guilty of it myself, and then I think you kind of, and again, they were actually talking about this on the Courtcast earlier. It's another YouTube channel, and they do weekly live streams at it's like 8 p.m. Eastern time on Tuesdays. A couple of young physicists on there. They do a pretty good job. Um, but they were talking about Occam's razor, and a lot of times it's like, all right, Occam's razor. What is it? Maybe the simplest answer is the answer. Why? Well, maybe nature is simple. I don't know. It, the simplest with explanatory power calls ultimately you can write down whatever you want, and it's numerology. Okay. When does it stop being numerology? Numerology is numerology until it explains more with less. If you can explain more with less and you haven't broken anything else, or perhaps you discovered something new, a new way to do things. Perhaps that new way to do things will explain even more. I mean, that's ultimately what we're hoping for. Okay, so a little bit of a review are there's ways you can write different things. Okay, so let's go with our good old friend alpha, the fine structure constant. All right, so alpha is defined as it is defined as elementary charge e squared divided by 4 pi h. I'm writing out h bar because I'm so used to typing it. H with our little bar there. See the speed of light, and then times epsilon naught, the electric constant. Okay, so that's a whole bunch of stuff. And you're like, all right, the fine structure constant, what this ends up being? This ends up being a dimensionless number like naught point, not 729, yada, yada, yada. Okay. So that's some stuff. You're like, all right. So we got elementary charge squared. So we got a charge squared and then times 4 pi, so like a circle thing, and h bar, an action thing, c, the maximum speed thing, times the permeability of free space, electric wise. I mean that's a lot of stuff. I mean maybe you could parse that. I could try it, but I'm like, okay, dimensionless ratio that seems maybe a little complicated. Okay, when you go to Wolfram Alpha, you end up finding out that this whole thing is actually just the Planck charge squared. So this whole expression is equivalent to, we can just do elementary charge on top, and then we're going to put a charge on bottom. So we're going to do Q sub P for the Planck charge. We're going to put our handy dandy brackets around the outside. We're going to square the whole dang thing, and it's going to be equivalent to that because it gives you the same number. Some people know that. I'm sure people, I think John Mackey or something like that, he was a physicist. He was on the Fractal Woman like a number of months back, and that was in his presentation. I'm like, oh, cool. It's like, I'm sure I'm not the only one that knows this because it gives you a dimensionless number. Okay. If you're dividing a charge squared number, this obviously has to cancel out the charge squared. But for some reason, this combination of constants and the 4 pi and stuff happens to be what gives you the fine structure constant. I'm just like the charge of an electron or a proton over the Planck charge, basically a 1 Planck units. You just square the whole dang thing, and then you get that. For those of you that have been following some of the other work at the Physics Monastery, you may have noticed if we don't square this, we get our friend Joe 1, that happens to have found a way to geometrically predict the fine structure constant to the Planck mass boundary, which is a very interesting thing. Oh, I'm sorry. Oh, we got K-Shell here. Welcome, K-Shell. Yes, yes. Oh, we got uncompetitive here too. Welcome, my friend. Let's see. I'm sorry. It's let's see what else we got going on. It's well, ultimately, it depends on how an individual can best think about. Because however you can best think of these things to the maximum degree that we're able to try to figure out these things and conceptualize it in your head, like 'cause my brain's going to be different than your brain and different than other people's brains. I mean, like that's just a given. But if we have better ways to parse these things, thinking of our own head, that's great. But you would also want to be able to hopefully communicate with other people because you might have figured out the most fantastical thing in the world. If you don't have the ability to actively communicate it with human beings, I mean, it's cool you figured it out, but it kind of goes to waste. Personal opinion there. Uh, yeah, no, boundaries are important. Oh, well, we might also be talking about Planckian boundaries here. All right, so where were we at? Oh, the whole reason I'm showing you this is there are certain relationships, and just as a real quick review, if you want to talk about the things that make up our realm of persistence, our colloquial, I'll say small u universe, because what are we even talking about? It's beyond that, as far as I know, there be dragons. I can't say, maybe turtles. Probably, yeah, it's probably turtles all the way down. Why do I say that? Because somewhere I have yes.
World is exists on the top of a giant turtle.
It's actually an old clip. That's like from 4 years ago. Wow, time sure flies. He was going over the history of where we kind of got the turtles all the way down.
It's turtles all the way down.
It's just hilarious just watching professional scientists like Stephen Wolfram. That's turtles all the way down. But he's at least understands
I should
that
learn all these memes.
it's not bad. Okay, so real quick side tangent. I literally just found that the whole Crossroads meme That whole, it's like, all right, you're going down a dirt road. You can go left to a path with a nice shiny castle. You can take the right path. You can go to the dark and sinister land. I found out that was from Yu-Gi-Oh! GX. I go on Twitter and I see it. I'm like, it really looks photoshopped, and people are showing all these different things, and I'm like, and then somebody links to the episode. I'm like, okay, I do kind of remember watching this episode. It was already posted 10 years ago. So I'm like, did they superimpose it on the official Yu-Gi-Oh channel like 10 years ago? Uh just where are we at? Hold on. I got it somewhere here. I went and checked and just took a larger screenshot of it. That's all. Up here. People really seem to like it. Okay. So let's present. You don't need to watch the video. I'm just because they post this up here. I'm like, okay, I could see that, but you could probably also Photoshop that in. And then I'm like, what is this? Because I also watched Yu-Gi-Oh! GX like 10 years ago. I was on a binge. I like the dueling thing back then. Oh God, Deep Lore makes even more sense now. Okay, it's from the official Yu-Gi-Oh! Channel 10 years ago. 1.1 million at Chaz arranged a duel with Alexis that he can prove his love to her, but Alexis has other ideas. It doesn't go well for Chaz. I'm just saying. All right. So there's your dose of meme history for at least the moment. All right, where are we at? Ah, yes, the whole science stuff and things. Where are we? Let's get a drink of water. All right. So we got this thing. We can simplify that into that. Okay. Since I'm a crazy person, had to submit an error to or some feedback to the people at Wolfram Alpha because I got an answer that I would love to be true, but we do not have enough scientific evidence for it to be evaluated as true. There's a whole thing I've been going on before about. All right, some people call this like one of the hierarchy problems, a hierarchy. I don't know what to refer to it as. I would just look at these things that I hear people say. And again, I'm sure I don't know all the group symmetries behind it and why it either breaks everything or doesn't make any sense. People like, well, what? Well, let's just play the dang video. Because one, I really like the video. Sorry. Anytime I can put some Dumbo Wubba thumping to any type of video, I don't care. It obviously doesn't matter to me. I should just be making more of those small little videos because one, it's fun to do, and two, if it helps get people to think, doesn't need to prove a point. It's just, oh, here's an idea. Have you considered this? Okay. So since I am a troll, let's right tab. Okay. This channel here. Okay. Again, we played this yesterday, but remember, my friends, you cannot predict the Higgs math. What's this picture we're looking at? This seems to be something that says if you take the Higgs boson mass and you divide it by the Planck mass and you square the whole dang thing, um, it equals the elementary unit of action, the reduced Planck's constant there, divided by joule second, which is basically uh, the unit used for it's basically the dimensions of the Planck constant. Now, maybe there's a problem with that, but essentially that's an effective one in the system. Okay. It also has a factor of like c squared in there, the speed of light squared. From our good old friend, E equals mc squared. Okay. It's in a different form, but wait a second. The Higgs boson, the Higgs mass over the Planck mass, the whole dang thing squared? Where have we where have we seen something that looks kind of like that? Oh look. The elementary charge over the Planck charge. We square the whole thing. What were we just looking at? Hey, the Higgs boson? our spin zero scalar boson over the Planck mass? Wait a second. Let's try this again. We got an elementary thing, okay, over a Planck thing. An elementary thing over a Planck thing squared. An elementary thing over a Planck thing squared. That's interesting. Okay, and we have it set equal to that, and we can argue about that. But it was hard to justify before because I'm just like, well, what am I doing? I'm just canceling out the dimension. Wait, how does this have any like meaningful factor? We'll get into that in probably in a little bit. I swear. Okay, hold on. Let's go here. Oh yeah, gonna have it in the yes. Oh, what did I even do? Go back. There we go. All right, Matt O'Dowd, take us away.
The hierarchy problem. And it's important because its solution is going to lead us beyond our current theories.
What's known as the hierarchy problem. That's the question of why the mass of the Higgs boson is so much smaller than the Planck mass.
So why is the Higgs boson, according to Dr. Hossenfelder, the hierarchy problem is why is the Higgs mass so much smaller than the Planck mass? Okay.
The hierarchy problem, put simply, is that we don't understand why the mass of the Higgs boson is so small.
The mass of the Higgs boson is a constant of nature. It's one of those three parameters in the Standard Model. This means you can't predict it.
So basically, it's, as far as we know, it's within our Standard Model. It's an elementary particle, so to speak, even though we're measuring a particle, but we believe it's a field there flowing throughout all things. We're getting some Star Wars vibes here. All right, continue, Doctor.
You just go and measure it.
From our understanding of quantum field theory,
Hold on, I'm sorry. Oh God, let's start that again. That was terrible. It was at 144p because I got Dragon Ball Super playing in the other window. So I'm that dude. All right, back to the hierarchy problem, Matt O'Dowd.
The hierarchy problem. And it's important because its solution is going to lead us beyond our current theories.
What's known as the hierarchy problem. That's the question of why the mass of the Higgs boson is so much smaller than the Planck mass.
The hierarchy problem, put simply, is that we don't understand why the mass of the Higgs boson is so small.
The mass of the Higgs boson is a constant of nature. It's one of those three parameters in the Standard Model. This means you can't predict it. You just go and measure it.
From our understanding of quantum field theory and the Standard Model of particle physics, interactions between the Higgs and the quantum vacuum should drive its mass up to enormous values. That would be catastrophic for our universe, and so we should be grateful that the small Higgs mass is somehow protected. We just don't know how it's protected.
So Charlie's comment could be thought of as a black object on a black background. So if you were to have a dark object on a dark background, I mean, that seems more akin to dark matter, so to speak. It's just we can't really make it out. When I think of the Higgs, I just think of, instead of just space, assume fluid, assume everything was like water. I think of the Higgs as kind of like almost like the honey in the water or something. I feel like it has almost like a viscosity to it. I know these are not the right words, but this is the best thing I can come to mind. It's kind of something a little bit thicker that helps add our mass to our stuff and things. So that's where I view it. And also, if you have honey instead of water, you'll literally put on more mass. So just that's how I view it there. Personal opinion again.
Supersymmetry doesn't change anything about this. The Higgs boson mass is still a free parameter in supersymmetric extensions of the Standard Model, and you still can't predict it.
That's interesting.
You may say, well, why not? And indeed, there's no reason why not.
Couldn't resist, mate.
Okay. So after some tub thumping and curb your enthusiasm aside, why am I showing this scene? Okay. Again. Okay. Got this stuff over that thing squared. Got this stuff over that thing squared. And basically, what I'm saying is you can rewrite things in a bunch of different ways. And again, this is a conjecture, so we don't know if it's true. Just because it says it's true doesn't mean it's true. It's true to 3 significant digits, aka the total number of known digits to the Higgs mass. Because we got 2 more, but they have error in them. Okay. And that's why I submit a ticket and say it wasn't true. But to argue against what it says, why? Because science, or at least the scientific method, you want to be accurate. Okay. All right. So we're done with that right now. All right. Boundary. I think it depends on how you kind of really want to slice it, or how because I hear a lot of folks saying different things, and if you're able to get to like the same answer or have the same explanatory power coming at from different angles, whether it's a hypergraph, whether it's a form of geometric unity, a quantum field theory, a string theory, whatever it might be, if you have something and it's able to explain a whole lot of stuff from a particular method, whether you're doing maybe kind of, and again, I'm not a quantum mechanic or anything, but if you're able to come at it from perhaps was it the quantum electrodynamics, the QED perspective, what are you looking at? Well, you're probably coming at it from a very charge-based thing. If you're coming at it from a probabilistic a method that sounds kind of stochastic, so it's probably maybe a temperature-based thing because now you got to apply Boltzmann's constant. You're going to try to do all these averages and everything, and they surprisingly work extremely well. I'm thinking we're getting glad. I think it's one of those things where a lot of different ideas, they're kind of all right on different levels and coming at it from different things. My whole big thing, and one of the reasons why I talk to lots of different folks, is I know I don't have the answer, but if I talk to enough smart folks and even some crazy folks, some crazy smart and some just crazy, myself included, I can probably steal enough ideas. And by steal, I'm like, oh, I learned this from this person. So when I do stuff like this, let me make sure I mention this person. Why? Because credit matters. It reminds me of that episode. Oh, hold on. We need a copy strike. Okay, we need to go to the Pirate King conference. Pirate King vote. Here we go. The Captain Peak scene. Oh yeah. Basically, when they're doing the keepers of the code, and they go around, they ask all the pirates who should they vote for, and everyone's like, oh, I vote for myself. I vote for my. Everyone's going around. That's why it never has any point. Why? Because everyone always votes for themselves because they're a bunch of pirates. And then at one point, where is it? Here we go. Here we go. We're gonna show this because we need a nice coffee strike. Okay. Here, Captain Barbosa is explaining voting for the Pirate King.
Reset. I call for a vote.
I vote for a man, of course.
Captain Cheval.
Oh, wait a second. Oh, they seem to be voting for themselves. What do we think, folks?
That's Frenchman.
Sisumbaji votes for Sisumbaji.
Mistress King.
Gentleman Jocard.
I mean, these people all seem to be voting for them. So here's one of the things. I hate voting for myself. It's one of those things. It seems so conceited. I understand that's one of those things. It's like, did I even vote for myself when I was running for Senate? Maybe, maybe. Oh God, think so. Oh, continue.
Elizabeth Swan.
Barbosa.
Villanueva!
Elizabeth Swan.
What?
Uh-oh. Uh-oh. Wait. What happened? Captain Jack voted for Elizabeth. You broke the dang thing. That's one of those things where it's like, all right, I have no idea what's going on. There's a whole lot of smart people. So it's like, when I come across that, it's like, it's okay. Even Dr. Weinstein, it's like, I wrote Dr. Weinstein an email because within his geometric unity things, there's, if you'd like to collaborate or work on this, please send me an email. I sent an email. I never got a response. And then that same week, that premiered source code 7. The next day they came out with the view on G2 results. I'm like, this dude predicted the view on G2 results. What's going on here? And I'm like, Thad Roberts. It's one of those things. It's you just kind of look at the receipts. Okay, I'm sorry. I've had that in my head. I needed to share it and get it out somewhere. All right. I think a lot of us get hunches, and a lot of us can kind of feel things. Because, like, to be fair, a lot of the actual physics stuff I actually learned is probably just from wrestling and working in the warehouse. It's because that's why I need to go through all the elementary stuff to learn all this stuff. And it's like, okay, I'm supposed to be here trying to like lay out a case. Let's actually finish laying out our case. So that last thing that we saw there was this was whole claim that, all right, well, if we have was it a joule second? Okay, that's the unit of action. All right, joule second. Oh, I wrote that the wrong way. Well, we could always write it the other way. My mind, Harry. So here, so okay. So just do this side squared, and we're doing m sub h, so the mass of the Higgs over m sub p, the Planck mass, that whole thing squared, and then this is h bar over a joule second. Okay. Yeah, that's fine. Okay. Well, back over here. All right. So the reason this and the one of the reasons why I put that in there is just because Wolfram Alpha comes at it as true, but it's only true for the 3 known digits of that. After that, we don't have enough data to actually say that. So it is rounding at some point there. So that is something to be cautious of. AKA we need higher precision experiments, probably about 7 high precision decimal places for a measurement of the Higgs to really try to see if there's some there. Okay. Because I mean, otherwise right now is if we only have the Higgs to 3 and you put in X kilograms and you just solve for X there, we know the Planck mass to 5, total 7 digits with error. We have H bar defined at 10 significant digits. So you can eke out about 5 significant digits for the Higgs mass and then put, like, it's a 6th for the 6th decimal place with an error of 2 in that last digit there. So maybe it's like 8, maybe it's 4. And this is just all according to the data that's out there then. I mean, I did do a little prediction out there with Thad's units for the Planck mass, H bar, where you can toss in like 15, 16, however many digits you want since it's the geometric answer. So I can get out to more than that, but just according to the data that we know, the data that we have, according to CoData and NIST and all the fancy generally accepted things, this appears to hold for the current amount of data. Okay, So why am I showing you this? Okay. I have this down here. Okay, let me just connect the MP there. Okay. So this is our box. Duh. It's a square with an X in it. Okay. So this box is in. Let me show. Let's see. That's probably changed a few things since then, but this is one of the more recent ones. Was from December. Okay. So let me share it with the class. All right. Window chemistry. So this is a list of 288 constants. Well, actually, a few more. Constants of nature. Okay. Why? Because it says constants of nature right there. Okay. That's cool. Now, what should we have here? Now, number one. Oh, he changed it. Oh, he put that there for freaking mention. Okay. But number one, what's this friend right here? Oh, that's a little c. What's that? Oh, that's the speed of light in a vacuum, because we have to say those words. Okay. What's this? That's the Planck length divided by the Planck time. Speed. Duh. Length per unit of time. Okay. Now, isn't that what the speed of light is defined as? Shouldn't it be specifically that? What is all this other stuff? Coincidentally, if you use the closed form for these Planck constants that Thad derived, it only gets about 7 significant digits. We know the speed of light to 9 significant digits. Where did the last two come in? Well, utilizing this method, and as we go to Wolfram Alpha to crank out some potential answers, we find it as this partition form. 1 plus the square root of the Giesing constant, aka the constant representing a volume of the minimal 3 manifold. We have our Jeux, so basically that's our friend over here. If we didn't have the square there, so it's basically the amplitude of the fine structure constant. So it's that minus the second answer, because it gives you 4 roots when you apply the hyperbolic equation. And then here's where we're getting to, that box. This box. Yes, that box. Don't worry, I'm not going to go through all the crazy stuff. But notice, this box is basically everywhere. Zoom out a little. So basically, the entire dang poster here, it's that box. It's that box. It's everywhere. What the heck is going on? That's basically our inversion boundary right there. Okay. Box, 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 box. Okay. Point communicated. All right, we can exit out of this. God, close window, please. Thank you. Okay. So now that I showed you, for those that are still here, the box might be important. What is the box? Okay. So that box, I had to double check before I came on to make sure that before I created this dang thing to make sure the box wasn't a lie, or at least my writing of it isn't a lie. Okay. But that is also equal to the same thing. So, this is a different. Oh, marker has matured better. Okay. So, M sub P, LP. So the Planck mass times the Planck length. And then it's divided by the Planck charge squared, Q sub P squared. Okay. So what are we saying? We're saying that this box is equal to this. To be fair, I think we may have modified, just put absolute magnitude values there just to take the number, because it's like, that's 7 significant digits in. How can we justify that? It's not like dimensional transmutation is an actual thing that people mention seems to happen that we don't really understand. Wonder if there's a relationship. Okay, we're not going to discuss that right now. Okay. I'm just throwing out all this stuff. It's all right. It's a very blasphemous show. All right. So the whole point of this Planck mass, Planck length is we're saying that this comes out to be, depending on your convention, either precisely 10 to the minus 7 or like 9.999992999 times 10 to the negative 8. I think I got that right. All right. So it's almost 10 to the negative 7, but not quite. Where are we at? Let's go to, we have the, do I have it here? Oh, let's go over here. Okay. So I'm sharing this up. Oh, screen. And our friend Wolfram Alpha. I can put this top of this marker back up. Oh, my other guy is here. You gotta cap those markers. You don't want it to lose its moistness. All right. So here we go. All right. So what the heck did we do? Since I like my brackets, we're gonna do the blank mass, blank blank. Literally, yes. You just type in the magic words over the blank charge squared. Okay. And then you get this 10 to the minus 7 number, kilogram meters per square, or ampere square. What? I do per second squared ampere. Yeah, blah. The ampere constant. That's why we crunch down notation. Just saying all those dang things is like, ugh. Okay, what is it? It's magnetic permeability. All right, it's the ability for you to be permeable by magnets or magnetic stuff. The interesting thing is the basic unit dimensions, it gives you this mass times length. Okay, so that's what we have over here. We've got mass times length. All right. And then, oh, if it's got a negative exponent, that means it's the denominator. So that means divided by time squared times current squared. Time squared times current squared. It's very interesting. Why is that interesting at all? Okay. Because originally, well, number one, while looking for some relationship for this, it's probably the craziest conjecture, is it may or may not have led to a four-dimensional platonic solid and its inverse. Yes, my friends, the hypericosahedron, the 600 cell, which apparently Nick Mers from the Wolfram Institute actually is doing a project on, because it seems to be the smallest set possible that he can model qubits. Okay, I'm not making this up. Like, literally, he used that. He found that a four-dimensional platonic solid happened to work best. The hypericosahedron. Yeah, you're D20 in 4 dimensions. Okay, and then its good friend, the hyperdodecahedron, the 120 cell, which has a lot of amazing geometric properties. It's literally a Swiss Army knife of the platonic solids. It's got all the different 3-dimensional platonic solids in it. Oh yeah, and do you want a little bit of irony? And the dodecahedron back in the time of the platonic solids in ancient Greece, it was viewed as the ether. Just the ether that permeates the heavens and stuff like that. And like, wouldn't it just beat all if we lived in the domain between the platonic solid and a higher dimension that represented the ether, but we totally don't live in the ether and intersect with the minimal thing to run qubits. It's but that's just a crazy conjecture. Let's try to make an actual substantive conjecture. Maybe see if we can get at the root of something. Because okay, if we got this times this, then charge squared is equal to that. Kind of like, oh, we get charge squared over here, and charge squared is equal to that. Huh. Wait a second. That's another way to actually look at that. God, thank you. That's so dumb. Okay, I'm gonna try to save myself by saying this is one of the reasons why we do these things, because you can look at something and it's like nothing's coming to me, and then you try to start explaining it, and it's like, wait, that thing that I'm trying to explain that I'm also looking at from that way is the same dang thing. It's the same. You can rewrite that as charge squared. Oh my god! And then you can just write it as time and current, or current time. Oh, this live stream was totally worth it. I have no idea how I didn't even notice this before. I literally must not have connected any neurons. I'm very excited. It's it's revelations and epiphanies. Yes, Charlie. It's well, here's the thing. Well, maybe it's commenting where the ethers where the Higgs. That's yeah, see, I don't know. I don't know enough about that. All I know is if we need some group theory to analyze to go through that, it would probably be at their intersections. It sounds like a good fit. Hey, look, what's going on? Yes, we are at the late night with memes, and that's a hello memes. Good to see you, my friend. Yeah, we're just doing this, and okay, Shell had popped in. All right, where are we at? Where does chart? Okay, so that was the first ever video that I did for the Physics Monastery because I got up there and I was it? I think it's probably my first or second time there. That I was giving presentation or something like that, or he had given a presentation before. And at some point, he's like, go up and say something. I'm like, what, me? Just a dude from the internet that came here. And he hands me a marker, and then I was a man with a marker and a microphone. So I went up and asked, what's the deal with charge? And I started to lay out a little bit of stuff that maybe I kind of knew or was parroting from YouTube videos and stuff. And then after like 10, 15 minutes, I'm like, all right, so what's actually going on here? I know Anastasia, that was one of her big things at school. It's like, what's charge? And nobody gave her a satisfactory answer to what's charge. We can figure out what charge is. We may figure out how magnets actually frickin' work. A little paraphrasing from, I think, the Insane Clown Posse. That's Professor Carroll actually did that. Did I add that in here? I need to add that to the media assets here. Oh, God, we have so much random stuff here.
Turtles all the way down.
I know there's a lot of turtles. Where else are we at? I think everything else is probably just really annoying and probably not appropriate for this venue. That's what Thursdays are for. Okay. The one other thing that I think is universal is
I have more information now, so the moral of the story is people were offended on the internet.
Yeah, basically.
I feel like that explains a lot. Okay. So back to what we're actually talking about. Oh no. Here's the thing. They always say science is a process. And I can guarantee you, somebody out there knew some of this stuff here, but it's like, all right, you go into Wolfram Alpha, this is the answer you get. It's like, all right, you get elementary charge over this, blah, blah, blah. It's what does that mean? I don't know. You're talking about a relationship, it's like, oh, well, this is the elementary charge. This is our boundary of charge. That we're relating boundaries, kind of like you were saying earlier. We've got that squared. So it's a squared relationship because one of the things I learned from Professor Sean Carroll's biggest ideas in the universe series was at one point he was talking about within physics. Oh, in physics, we'll look at the relationship between different things, and sometimes we look at the relationship. If that doesn't make sense, you square it. You see what happens. So it's like, all right, you do that, and you get that, and everything. To be fair, even Professor Feynman, I think he tended to refer to it. He's like, uh, oh, the fine structure constant or whatever. He referred to it as the non-squared version. He's like, my friends like to refer to it as the inverse of its square or something like that, because apparently 1 over or 137 is a lot sexier than like 11.7 or whatever. It was, I think that was a more of a cosmetic thing because you can go back and forth. You can take square root, whatever. Uh, you should probably keep track of that because it doesn't always line up. So uh, you need to make sure whatever the logic is flowing. And ultimately, yeah, we use math and different symbols and relationships to do different things. But it's like before back in the day, you need to, right? We need to have encyclopedia, our car, our printout of all the different things to put into our calculator. No, but for the days of calculators, Newton literally invented calculus that will help him work well through the science and everything. Leibniz probably invented it a little bit earlier and stuff, but Newton was more famous and powerful and apparently allegedly kind of a dick. So he probably took most of the credit for it. But I digress. It's like, no, science is a process. And there's a lot of other people, and there's a lot of folks that, like, we hear certain names, you're like, oh, this person was so famous and stuff at the time. Yeah, you get some of the Einsteins, and yeah, Einstein kind of got played out, and it's like, yeah, we assume, because a lot of times it was also, he was a very endearing gentleman. He seemed to be very kind and everything. I did a little story about somebody meeting him and like to listen to some classical stuff, and he spent all this time to help him attune because he's like, I don't like classical music and stuff like that. And like, it, apparently, he was a kind person, so that story seemed plausible. I have no idea if it's true, but a lot of times we'll take different people of history and maybe occasionally embellish or paint them in very particular lights. And that's where our memes come from and everything. Um, but I think apparently Einstein kind of realized a lot of folks were like, yes, we're cheering him around. It's like, you're kind of doing that idolatry thing. Might want to be careful about that. But you realize there's so many folks out there that are behind the scenes that some folks it's like, oh, they're big names nowadays. And it's like, oh, they died penniless and alone. Some of them took their own lives. It's very sad. And then there's all the other people that don't even make it or weren't even in the history. But see, one of the things that gives me hope now is when the internet archaeologists, assuming we don't destroy ourselves, 1,000 years go back, they start going through this early video technology of YouTubes and stuff like that. It's like, well, everything was time stamped, dated, and recorded. And it's like, all right, we have like logs of the chat and stuff, so you can actually see the process that people are going through. I think that's a really cool thing. It's one of the reasons I think Professor Wolfram likes doing his live streams. It's just because he gets to get that stuff out there, and and then when Professor Wolfram is sadly no longer among us, we might not even notice. Because there might be an AI Wolfram that's so good because he has all this personal data on stuff. We'll still see Stephen Wolfram doing live streams for another millennia. That might be kind of cool, but I won't be around. But it's just one of those things where it's like, oh, you acknowledge where different things happened, and sometimes it's just interacting with folks all of a sudden, just a random neuron click. I know occasionally Thad will say something. It's like, you speak words, and then I get ideas, and it's like, oh no, I just looked at the thing and I just asked like a silly question. Maybe it wasn't as silly as I thought, and you never know. Really. Well, science is a process. Reality is, well, that's hard to argue with. Uh, uh no, that's see, that's the thing. A power positivity, because there's a lot of negative stuff out there. Don't get me wrong. I get my daily dose of negativity. I have friends that do different drama, and I'll usually scroll through the headlines and I'll look through them. I'm like, okay, what's this? Maybe click on the occasional article. Most of them now seem paywalled and everything. So it's like, I mean, I'd love to just comment on this, but I honestly, depending on what it is, I don't have enough ideas. Some things I just don't really care about. I'm like, all right, that's a video game. It's the baboon, that's the new Monster Hunter. I might need to reach out to some friends and maybe just get some thoughts on some different panels there. But oh, jeez. Well, see, the thing is, apparently, there's different ways to pass on things. You can do it genetically through different reproductions and stuff like that, and then there's the ability to do it mimetically too. Because Richard Dawkins, I think in chapter 4 of The Selfish Gene, he introduced the concept of memes before we had all our little short, like text-based things. Well, to be fair, memes have been around technically forever. Uh, but the concept of something that gets passed on. That's why I was showing you that Yu-Gi-Oh meme earlier. The Crossroads meme was actually from an episode of Yu-Gi-Oh GX that I watched like a decade ago. I didn't realize that until literally earlier. I thought that was kind of cool. Somebody pointed that out. I'm like, wait, that's an actual Yu-Gi-Oh card? Kind of disappointed that I forgot about it. Uh, and I digress. Okay, so what oh jeez. Okay, I'm kind of mind blown right now. That's charge squared. So Planck charge squared is equal to 4 pi h bar c elementary constant. And if that's also equal to the Planck time times the Planck current, means the fine structure constant we could rewrite. Also, so this will be elementary charge squared. And that's over like time squared. Oh wait, no. I don't even need that. No, I'd square the whole thing on the outside. This gets even better. All right. So elementary charge over Planck time, and then Planck current. All squared. Boom. Feel like this is like a cheat code for a game. Or I'm trying to do like a Hadouken or something. Because it's like, wait. So this whole dang thing, Planck charge is time times current. Charge is time times current. Time times current. Current times time. Okay, it's still kind of confusing in a way. Okay. The time current. Oh, that sounds cool. Time current. Oh, I feel like we're getting into like good Doctor Who here. I've never actually really watched Doctor Who. Maybe like one episode. Um, so elementary charge over time current squared. That just sounds pretty to me. Huh. That's interesting. You know, my mind's kind of blown here. I mean, it's one of those things. You look at these things, it's like straight up, and I'm like, that's why I'm like, I had to go to Wolfram Alpha and submit a community note because it's like, I'm like, somebody had to have noticed. Is it really just because people said you couldn't do it? So there's no looking at it? I mean, maybe Wolfram Alpha hasn't been updated with this until the past few years, but I'm just like, if you're asking the question, why is the Higgs mass divided by the Planck mass like 10 to the minus 17? Like, why is it so small? It's like 10 to the minus 17 times smaller. What we should actually be doing it squared relationship. It gets the first 3 digits and the magnitude of h bar. I mean, like, do, do people know that? I mean, Wolfram Alpha just kicked that out for me, and they actually have to probably asking thousands and thousands of questions, like with h bar and h bar magnitude-ish thing coming out. Maybe it's just like, oh, I recognize those digits. I recognize that power. What happens if I cancel the dimension? It returns true. And I'm like, we can't say that. We don't have enough digits for this yet. Do I want it to be true? Absolutely. I think it would be kind of cool. I just need to finish writing my actual first academic paper rather than just talking about it on the internet. I feel like here is publishing too, because you can publish to YouTube. That's literally what it says you do. I really realized that was a thing with the internet. At one point, Facebook had changed, but I think probably back around 2013 or something. Oh, God, that was 12 years ago now. Jeez, I'm ancient. But they had changed something because before they had post. And at some point, they changed it to publish. Because I think they wanted to raise people's conscientiousness of just, you're publishing something to the internet. Maybe you should think before you publish. It was a low key kind of psychological thing, but it got my old noggin a jogging. Like maybe we should think. And then again, people come in where it's like if you've been born into a world where it's like, well, there's always been a Facebook, there's always been social media, and that's all you've ever known. That's a much different society than being like, I don't want to say a free range kid, but it's like we went outside. We picked up sticks and we battled monsters, usually large trees or boulders, with those sticks. God, it was fun. Ah, wasted youth. Something like that. Oh, you got that right, Glug. Yeah, no, time does pass in very interesting ways. It's okay. It's okay. I think it's about the company and the ride. Substances that form barriers between different regions. See, that's very interesting. We're gonna. Well, to be fair, Charlie, actually, on the dark and light side, if you actually compute this, you get a positive and a negative answer. That's kind of silly, but when you could just write this as straight brackets and say we're taking the absolute magnitude. But I think a lot of these things you actually do get positive and negative answers, and sometimes it's the antiparticle. I think that's how they do it. Is there an anti-Higgs? Is that what it is? No, that doesn't make sense. It doesn't have charge because the only difference is charge or spin, and the Higgs has no charge or spin. Huh. It's another thing to think about. But okay, I'm sorry. I just gets me all noggin the drunk. We gotta do a tiny bit of math. Hold on, I still got this guy here. I got this. Like charge. So just give us these dimensions. So it's time current. Time current squared. I feel like that should be a TV show. Time current. What is that? Times current. Okay. But what is current? Let's do that. Because this is it's the conversion between them, but it always confuses me because I kind of learned it one way. It's kind of like when I learned how to ride a motorcycle, I learned like incorrectly, and then I nearly failed the actual course. Let's try this. Let's do current. Let's see what comes up. Current. Oh wow, the lag. There must be. Yeah, it's late at night over here. There must be a lot of LLMs querying. All right, electric current, physical quality, symbol. Yep, big I. That's why I use that thing. Okay, the big I. I can try to pretend to electrodynamics myself. Memories. Current, the standard unit for electric current is. Oh, I didn't share back. Is the ampere. Why? So I think it was that dude that kind of figured it. So ampage, ampacity, current. Ah, critical current, all current. Okay. So it's amps. Because it's not the voltage that gets you, it's the amps. That's what I've heard. Again, I'm not a licensed electrician, but I just remember it's like, nah, you can have like do the Tesla thing. It's like 500,000, 1,000,000 volts, and it's like he's perfectly fine there. It's like, why? Well, it's 1 amp going through you at the that's don't get hit by an amp. Okay, so Planck current. How do they define it? Oh wow! Look at this thingy. That's crazy. Oh wait, it's got big G in there. Is that in the Planck chart? Doesn't have any in charge. It's charge time. Yeah, E naught H bar. Huh. The Planck current has big G. Okay, yeah, here's where we get at like 2 pi, 2 square pi. So we get 2 square pi. Excuse me, 2 root pi. 2 root pi times the square root of the speed of light to the 6th power times the electric constant over big G. That's interesting. This number seems a little familiar. Okay. Well, that appears to be about the Planck force. Let's see. That's 2 times the Planck force. Because there's 2 wires. Now I see why retired engineers love this stuff. And I don't know, maybe we're just too dismissive of different people. I have no idea. I'm out here basically claiming, conjecturing away that, I have a way to predict the Higgs boson mass, even though you're not supposed to do that. And Wolfram Alpha said it was true. I'm sorry. I submitted the ticket to get that fixed, but all right. So it's after midnight now. We've gone for over an hour. This has been fun. Well, I got some more work to do, and other than that, should be back tomorrow. And feel free to interact with any of this content however you find fit. Other than that, that's all we really got. So, peace out, everybody. Take care of yourself. It's a crazy world out there, and just hoping for the best. 2025, I think it's gonna be a heck of a time to be alive. Catch you all later.